While you're standing on solid ground right now, a massive slab of rock beneath the ocean floor is slowly sliding under an island nation. Deep beneath the dark water, two giant pieces of the Earth's crust are grinding together with immense force. Most of the time, this movement is completely invisible, but right now, a sudden shift has sent deep shockwaves rippling through the land. Something hidden far underground has finally snapped, and the ground above is starting to tremble. If you love exploring the hidden mysteries of our planet with real science and no sensational hype, consider hitting the subscribe button right now. Joining our community means you will always be the first to uncover what is truly happening deep beneath the Earth. Now, let us explore this fascinating geological mystery together. To really understand what just happened, we first have to take a look at where New Zealand sits on the map of our world. Most people think of ground as solid and unmoving, something that stays still beneath our feet forever. But the surface of our planet is actually broken into huge pieces called tectonic plates, which fit together like a giant floating puzzle. These massive plates move very slowly every single day, traveling at about the same speed your fingernails grow. New Zealand sits in a very unusual and dangerous spot on this planetary puzzle. It rests directly on top of the boundary where two of the largest plates on Earth crash into each other. On one side, you have the giant Pacific Plate, which covers a massive part of the ocean floor. On the other side, you have the Australian Plate, carrying the entire continent of Australia and parts of the ocean surrounding it. Because these two giant slabs of rock are moving in different directions, they collide constantly. In some parts of the country, one plate tries to push straight past the other side by side. In other parts, one plate is forced to dive deep down underneath the other, into the hot mantle of the Earth. This meeting line makes New Zealand one of the most seismically active places on the entire planet. To make matters even more interesting, New Zealand is actually the visible peak of a vast submerged continent called Zealandia. Millions of years ago, Zealandia was connected to the supercontinent of Gondwana, alongside Australia and Antarctica. Over time, powerful forces inside the Earth stretched the crust until Zealandia broke away and sank beneath the sea. Today, roughly 94% of Zealandia remains hidden underwater beneath the Pacific Ocean. The small fraction of Zealandia that sits above water forms the North and South Islands of New Zealand. Because this landmass sits squeezed right between two colliding tectonic plates, it is constantly being reshaped, uplifted, and broken by geological forces. The very mountains that make the country so beautiful exist only because tectonic forces are continually shoving rock upward toward the sky. Scientists often refer to this entire region as part of the famous Pacific Ring of Fire. The Ring of Fire is a huge horseshoe-shaped path around the edges of the Pacific Ocean, where most of the world's earthquakes and volcanic eruptions happen. Millions of people live right on top of these active zones, often without realizing how much energy is building up directly beneath their houses. Every year, New Zealand experiences thousands of small tremors that people never even feel. However, every once in a while, the pressure deep underground becomes too great for the rock to hold. When the rock breaks, all that trapped energy releases in a fraction of a second, sending powerful waves through the ground. That is exactly what happened recently near the small coastal town of Te Araroa, located on the east coast of New Zealand's North Island. Did you know that the Earth beneath us is moving every single second of the day? Drop a comment below with the location where you live, and let us know if you have ever felt the ground shake beneath your feet. If you enjoy learning how our planet works, hit the like button so more people can discover this story. When the earthquake struck near Te Araroa at roughly 8:30 in the evening, thousands of people felt the ground start to sway. Instruments set up by GeoNet, the official scientific agency that tracks earthquakes in New Zealand, registered the event at a magnitude of 5.9. Within minutes, over 5,000 residents across the region reported feeling the vibration from quiet coastal towns to larger cities further inland. For many people, a magnitude 5.9 earthquake might just sound like a simple number on a news screen. But on the scientific scale used to measure earthquakes, every full number jump means 32 times more energy is released. A magnitude 5.9 earthquake releases energy equivalent to thousands of tons of high explosives going off deep beneath the surface. It is a massive display of planetary force that instantly catches the attention of scientists around the world. When experts first saw the initial data pop up on their screens, they expected the quake to be a standard shallow surface rupture. Most common earthquakes that cause visible damage happen very close to the surface, within the top 10 kilometers of the Earth's crust. But as the automated computers processed the seismic waves, a very different picture began to emerge. The sensors revealed that this earthquake did not happen right near the surface. Instead, the rupture occurred deep down, roughly 39 kilometers beneath the seabed off the coast. That depth meant something very specific to geologists studying the area. It meant the quake did not happen inside the top crust, but rather deep within a massive underground collision zone known as the Hikurangi Subduction Zone. This finding immediately changed how experts viewed the event. A shallow earthquake usually affects a small area very intensely, causing localized damage to buildings and roads. But a deep subduction earthquake spreads its energy out over a much wider region, shaking a vast area while signaling that major movements are taking place deep within the planet's internal machinery. When an earthquake ruptures deep beneath the ocean, it sends out two distinct types of vibrational waves through the rock. The first to arrive are called primary waves, or P waves, which squeeze and stretch the rock in the same direction the wave is traveling. P waves travel extremely fast, but they rarely cause major damage and feel like a sudden thump or sharp jerk. Following right behind the P waves are the secondary waves, or S waves, which shake the ground from side to side like a moving rope. S waves travel slower than P waves, but they carry much more energy and cause the swaying motion that people feel inside buildings. By measuring the precise time gap between the arrival of P waves and S waves across multiple stations, scientists can calculate the exact origin point of the quake. When you picture an earthquake, do you imagine the ground cracking open at the surface, or do you think about deep forces miles underground? Tell us your thoughts in the comments section below, and do not forget to subscribe if you want to stay updated on major Earth discoveries. To understand why a deep quake near Te Araroa concerns geologists so much, we have to look at the Hikurangi Subduction Zone itself. This zone is an immense underwater boundary where the Pacific Plate slides down beneath the North Island of New Zealand. It extends for hundreds of kilometers along the east coast, stretching from the top of the South Island all the way up toward the Kermadec Trench in the north. It is widely considered by scientists to be the single largest natural hazard facing the entire country. For a long time, early geologists believed that subduction zones moved smoothly like a giant conveyor belt. They thought the ocean floor simply glided beneath the land without getting stuck, releasing tiny amounts of friction continuously. But modern science has proven that idea completely wrong. Instead of sliding smoothly, the two giant plates get locked together by immense friction along their contact zone. As the Pacific Plate keeps trying to move westward at about 4 centimeters every year, the locked section refuses to budge. As a result, the land above gets dragged downward and squeezed like a giant metal spring being compressed over hundreds of years. Eventually, that spring has to release its energy. When the friction finally fails, the upper plate snaps backward in a matter of seconds, pushing the land upward and shoving the ocean water above it. This sudden snap can trigger massive earthquakes rated magnitude 8 or higher, capable of generating powerful tsunamis that can cross entire oceans. Scientists monitoring the Hikurangi Subduction Zone have discovered that this boundary has stayed locked in certain areas for centuries. That means hundreds of years of built-up pressure are currently stored inside the rock right off the coast. Every moderate earthquake, like the 5.9 event near Te Araroa, acts like a tiny creak in a door that is holding back an enormous amount of force. Subduction zones around the world share this exact same dangerous mechanism. In December 2004, a massive subduction zone off the coast of Sumatra, Indonesia, snapped after centuries of locked pressure. That magnitude 9.1 megathrust earthquake shifted the ocean floor by several meters, generating devastating tsunami waves that traveled thousands of miles across the Indian Ocean. In March 2011, a similar subduction event occurred off the coast of Tohoku, Japan. A magnitude 9.0 earthquake shook the region for nearly 6 minutes, causing the seafloor to jump upward by over 7 meters. The resulting tsunami inundated coastal towns and provided a stark warning to other nations sitting on active subduction zones. Because New Zealand sits on a subduction zone with similar physical characteristics to Japan and Sumatra, geologists treat every event along the Hikurangi margin with extreme seriousness. They know that understanding the current state of stress along this fault line is vital for preparing coastal communities for future events. Before we look at the strange pattern scientists uncovered inside this fault zone, here's a quick question for you. Have you ever heard of slow-motion earthquakes that take weeks to finish instead of seconds? Share your reaction in the comments below, and give this video a like if you find Earth science fascinating. What makes the Hikurangi Subduction Zone even more mysterious is a phenomenon discovered only in recent decades called slow slip events. In a normal earthquake, rock breaks violently, releasing energy in seconds and shaking the ground violently. But during a slow slip event, the two plates slide past each other very slowly over days, weeks, or even months. Scientists originally thought that fault lines could only move in two ways, either stuck tight until a big quake, or creeping along smoothly with no seismic activity at all. The discovery of slow slip events completely shattered that old belief. Researchers realized the Earth has a secret middle ground where massive amounts of energy can move without anyone on the surface feeling a thing. Instruments placed across New Zealand, including hyper-precise GPS stations anchored deep into bedrock, track these slow slip movements continuously. The GPS nodes can detect movements as small as a single millimeter. Using this technology, scientists noticed that parts of the Hikurangi Subduction Zone undergo slow slip events every 1 to 2 years, moving the land by several centimeters over a few weeks. If a slow slip event released all its stored energy in a single fraction of a second, it would register as a magnitude 7.0 earthquake. But because the energy is released so gradually over several weeks, no destructive shaking occurs at the surface. People living directly above a slow slip event go about their daily lives completely unaware that the ground beneath them is sliding centimeters out of position. Here's the vital detail that researchers pay closest attention to when these events occur. While a slow slip event releases energy safely without causing damage, it also transfers that released stress onto neighboring parts of the fault that remain tightly locked. It is like releasing one strain on a rope, which immediately makes the remaining strands pull much tighter. When the M5.9 earthquake struck off the coast, scientists immediately rushed to analyze whether it occurred inside a slow slip zone or within a locked zone. Their analysis showed that the quake hit right near the edge where slow-moving rock meets completely stuck rock. That boundary line is one of the most dangerous places underground because stress concentrates right at the transition point. In recent years, researchers placed advanced sensors directly on the ocean floor along the Hikurangi Trench to study these deep interaction zones. These seafloor instruments measure tiny changes in water pressure caused by the ocean floor rising or sinking by mere millimeters. The data gathered from these underwater observatories has given scientists an unprecedented look into how water and rock interact deep underground. Geologists found that fluids trapped deep within the subduction zone play a massive role in regulating how faults move. Water trapped inside the porous sediment acts like a lubricant, allowing plates to slide past each other in slow slip events. But where fluids are absent or blocked by dense rock layers, the friction remains extremely high, keeping the fault tightly locked until it breaks violently. Do you think scientists will one day be able to predict exact earthquake times using GPS data? Drop your thoughts in the comments below and hit that subscribe button to join our community of curious minds exploring the mysteries of our world. To see how these complex fault systems can behave in unexpected ways, we only have to look back at New Zealand's recent history. In November 2016, a massive magnitude 7.8 earthquake struck near the town of Kaikōura on the South Island. What happened during that event shocked geologists around the globe and changed earthquake science forever. Before the Kaikōura event, standard scientific models assumed that an earthquake usually stayed on one single fault line. Experts believed that once a break started on one fault, it would travel down that specific crack until it ran out of energy, but Kaikōura proved that nature does not always follow simple textbook rules. During that single event, the rupture jumped across at least 20 different fault lines underground, tearing through them like a falling row of dominoes. Some of those faults had never even been mapped by geologists before. The earthquake was so powerful that it physically pulled parts of the South Island several meters closer to the North Island, and lifted parts of the rocky seabed 2 meters above the tide line in seconds. The seabed uplift around Kaikōura was so dramatic that entire marine ecosystems were instantly exposed to the open air. Crayfish, sea kelp, and paua shells that had lived underwater for centuries were suddenly sitting high and dry on fresh rock platforms above the high tide mark. It was a stark visual reminder of how quickly tectonic forces can permanently change the geography of a coastline. The lesson from Kaikōura was loud and clear. Fault zones in New Zealand are deeply interconnected in ways scientists are still working to fully map. An event on one fault line can easily set off a chain reaction on adjacent faults nearby. This interconnected network is why a magnitude 5.9 earthquake near Te Araroa gets so much detailed attention from research institutions like GeoNet Science. Another historic event that reshaped New Zealand occurred in February 1931 near Hawke's Bay on the east coast of the North Island. A magnitude 7.8 earthquake struck the region, destroying major towns and causing severe loss of life. That quake uplifted huge areas of land, converting an entire shallow lagoon into dry ground that today forms part of the region's airport and farmland. The Hawke's Bay event showed how vulnerable communities along the east coast can be to sudden tectonic movements. In the decades since, scientists have worked tirelessly to study the geological records left behind in coastal swamps and ancient lakebeds. By digging deep core samples, researchers can identify layered deposits left behind by ancient tsunamis and prehistoric earthquakes that occurred thousands of years ago. These core samples reveal that the Hikurangi Subduction Zone has produced massive megathrust earthquakes every few hundred years throughout history. The geological evidence shows that past events triggered substantial coastal land shifts and large tsunami waves that battered the coastlines. Understanding this deep history gives modern scientists a clearer perspective on what the subduction zone is capable of producing in the future. Further south on the island nation sits another massive feature called the Alpine Fault. The Alpine Fault runs right down the spine of the South Island for over 800 kilometers. Geological records show that the Alpine Fault ruptures in a major magnitude 8 earthquake roughly every 300 years like clockwork. The last time the Alpine Fault had a major rupture was in the year 1717, which means it has been quiet for over 300 years. Geologists estimate there is roughly a 70% chance that the Alpine Fault will rupture again within the next 50 years. With pressure building along both the Alpine Fault and the Hikurangi Subduction Zone, every moderate quake provides key clues about how strain is moving across the entire country. If you were living in a country surrounded by active fault lines, would you feel nervous or prepared? Comment your answer below and share this video with a friend who loves learning about natural events. To understand how scientists measure these deep movements so accurately, we have to look at the technology deployed across New Zealand. The National Monitoring Network, operated by GeoNet, relies on hundreds of seismic stations placed on mountains, islands, and in deep boreholes. These sensors continuously record ground vibrations and transmit data in real time to research centers in Wellington and Auckland. When a seismic sensor detects movement, complex algorithms calculate the origin time, location, depth, and magnitude of the earthquake within seconds. Automated systems immediately post this information online, so citizens and emergency workers know where the shaking occurred. This rapid data sharing is crucial for initiating emergency response plans and evaluating potential tsunami threats. In addition to seismic sensors on land, New Zealand utilizes deep sea pressure sensors known as DART buoys deployed out in the Pacific Ocean. DART stands for Deep Ocean Assessment and Reporting of Tsunamis. These sophisticated systems rest on the ocean floor, miles below the surface, measuring tiny changes in water pressure caused by passing tsunami waves. If an earthquake shifts the seafloor and creates a tsunami wave, the underwater sensor detects the sudden change in water height, which can be as small as 1 single millimeter. The sensor immediately sends an acoustic signal to a floating surface buoy, which then beams the alert to satellites. Within minutes, emergency management teams receive precise data on the wave speed and direction, allowing them to issue coastal evacuations before the wave reaches land. Scientists also rely heavily on satellite radar technology known as InSAR, which stands for Interferometric Synthetic Aperture Radar. Satellites orbiting high above the Earth bounce radar signals off the ground surface at regular intervals. By comparing radar images taken before and after an earthquake or slow slip event, scientists can create detailed color maps showing exactly how much the land moved down to the millimeter level. These satellite maps reveal hidden patterns of ground warping that would be completely invisible from the ground. They show how large areas of land bulge upward, tilt sideways, or sink downward in response to deep movement along subduction zones. This technology allows geologists to map the exact boundaries of underground fault breaks with remarkable clarity. Right now, as you listen to this, scientists are closely monitoring the region around Te Araroa using an advanced network of sensors. Floating ocean buoys, deep underwater pressure gauges, and seismic stations anchored into solid ground are recording every tiny vibration traveling through the crust. The goal is to track aftershocks and determine if the Earth is settling down or shifting further. In the days immediately following a 5.9 earthquake, hundreds of smaller aftershocks naturally occur as the crust adjusts to the new position. Most of these aftershocks are small, ranging from magnitude 2 to 4, and are only picked up by sensitive science equipment. But each tiny rumble gives scientists a clear picture of how stress is redistributing itself underground right now. If the aftershocks steadily decrease in size and frequency over time, it usually means the crust is settling back into a temporary state of balance. But if aftershocks start spreading into nearby locked sections of the subduction zone, it signals that pressure might be building up in a new location. Geologists use complex computer simulations to map these stress changes in real time. When stress shifts from one section of a fault to another, it can sometimes trigger a secondary rupture days or weeks later. Geologists call this phenomenon stress triggering. By calculating where stress increased and where it decreased following the M5.9 quake, researchers can identify neighboring fault segments that might have been brought closer to their breaking point. What makes this ongoing situation so fascinating is that we are watching geological forces shape our world in real time. Mountains in New Zealand are not just ancient structures standing still. They are actively being pushed higher every single year by plate collisions. Valleys are widening, coastlines are shifting, and the seafloor is slowly creeping downward into the deep earth. The Southern Alps, on the South Island, are rising by several millimeters every year as the Australian and Pacific plates grind together. However, erosion from heavy rain, snow, and ice constantly wears the mountains down at a similar rate. This continuous tug-of-war between tectonic uplift and weather erosion creates a dynamic landscape that is constantly renewing itself. In the North Island, subduction forces melt rock deep underground, feeding a volcanic line that includes active volcanoes like Mount Ruapehu, Mount Tongariro, and White Island. The same subduction process that generates deep earthquakes like the one near Te Araroa also provides the magma that fuels these impressive volcanic centers. Earthquakes and volcanoes are simply two different expressions of the same deep planetary engine. Living alongside these powerful forces requires incredible human resilience and engineering. New Zealand has developed some of the most advanced building codes in the world to ensure structures can withstand intense shaking. Base isolators, Flexible foundations and lightweight materials allow modern buildings to sway safely during quakes rather than collapse. Base isolation technology was actually pioneered in New Zealand during the 1970s. It involves placing flexible rubber and steel bearings between a building foundation and the structure above. When an earthquake hits, the ground moves back and forth violently beneath the building, while the flexible bearings absorb the shock, keeping the floors above relatively still and safe. Modern bridge designs also incorporate flexible joints and energy-absorbing steel dampers that prevent spans from falling off their supports during major shaking. Lifeline infrastructure, including water pipes, gas lines, and electrical grids, is increasingly built with flexible connections that can bend and stretch without snapping when the ground shifts. Scientists are also constantly improving early warning systems. While predicting the exact minute an earthquake will happen remains impossible, modern sensors can detect the fast-moving primary seismic wave that causes no damage. Automated systems can then instantly send alerts to smartphones seconds before the slower, destructive secondary waves arrive, giving people precious time to drop, cover, and hold on. Early warning systems can also automatically shut down high-speed trains, halt factory assembly lines, open fire station doors, and switch hospital backup generators on before the severe shaking begins. Even a few seconds of advance warning can save countless lives and prevent major infrastructure failures when a massive rupture occurs. Public education plays a vital role in earthquake preparedness across New Zealand. Regular national drills teach adults and school children exactly how to respond when shaking starts. Coastal communities are lined with clear evacuation routes pointing toward high ground, ensuring people know where to run if a strong earthquake signals a potential tsunami. The golden rule for coastal safety in subduction zones is simple. If an earthquake is long or strong, get gone. If ground shaking lasts for more than a minute or is strong enough that it is hard to stand up, residents are instructed to move inland or to higher ground immediately without waiting for an official tsunami siren or emergency text alert. This self-evacuation rule exists because a local subduction earthquake can generate tsunami waves that reach the coast in less than 15 to 20 minutes. That leaves very little time for official agencies to issue formal warnings, making immediate action based on natural warning signs the most effective way to survive. Community readiness also involves maintaining emergency supply kits containing water, non-perishable food, flashlights, radios, and medical supplies. When major earthquakes disrupt power grids, water networks, and roads, being self-sufficient for several days allows emergency services to focus on high-priority rescue operations. Understanding how our planet behaves beneath our feet helps demystify these sudden natural events. Rather than viewing earthquakes purely as terrifying disasters, geological science allows us to see them as necessary physical processes that keep our planet active and dynamic. Without plate tectonics, Earth would be a geologically dead world like Mars or the Moon, lacking continuous atmosphere and ocean recycling. Plate tectonics helps regulate Earth's climate over millions of years by cycling carbon between the atmosphere and the Earth's interior. Volcanoes release carbon dioxide into the air, while subduction zones carry carbon-rich ocean sediments back down into the mantle. This natural global thermostat has kept Earth's temperature within a habitable range for billions of years, allowing life to thrive. The study of earthquakes near active fault lines like Te Araroa contributes directly to global scientific knowledge. Researchers from all over the world travel to New Zealand to collaborate with local geologists, sharing data and testing new sensor technologies. Lessons learned along the Hikurangi Subduction Zone help protect communities along subduction zones in North America, South America, Japan, and the Pacific Islands. As instrumentation becomes more sensitive and computer modeling becomes more powerful, our ability to map underground stress patterns improves every year. Scientists can now run detailed supercomputer simulations that model how seismic waves travel through complex three-dimensional rock structures, revealing which neighborhoods might experience amplified shaking during future quakes. Ultimately, studying earthquakes like the one near Te Araroa reminds us of how dynamic and alive our planet truly is beneath the calm surface. The crust we build our lives upon is constantly moving, driven by deep heat engines left over from the formation of the Earth billions of years ago. Understanding these movements is key to keeping communities safe and respecting the powerful natural world around us. Every tremor recorded by seismic stations tells a small part of an ongoing story that began billions of years ago and will continue long into the future. By paying close attention to these subtle planetary signals, humanity continues to unlock the deepest secrets hidden beneath our feet. If you found this breakdown insightful and want to explore more incredible science and Earth mysteries, please subscribe to the channel, click the notification bell so you never miss an upload, drop a comment with your thoughts on this discovery, and share this video with someone who loves real science stories. Thank you so much for watching. Stay curious, and we will see you in the very next story.